Now that you all are experts at mean, median, mode, and range, we're going to get into a little bit more advanced stats. If you've taken a stats class, then this will be a review for you. But I know a lot of you haven't, or maybe you're just starting your class. So this is going to be about standard deviation, which is going to be a really important concept in this class that we're going to use off and on all year long. Okay, so basically what it is it's a calculation that you can make off of your data, okay? And it's a way to see how clustered your data is. And so once you make this calculation, you're going to get a number value. And the lower the number, it means the closer your data points are to the average, or to the mean. And the higher the number, the further away these data points are to the mean. So basically, the lower the standard deviation, the more clustered your data is. And so it's kind of like, it's kind of more consistent. And the higher your standard deviation is, it means there's going to be a lot more variability, and maybe, you're not seeing consistent results. Okay. And so if we're not seeing consistent results, so we have a high standard deviation, it's really hard to make a claim, right? Because our data is kind of all over the place. But if our standard deviation is really low, that means we're getting roughly the same results every single time. And so we can be a little bit more certain about making a claim. Okay. So here's the equation. Oh, it's also on your equation sheet. I don't want you to freak out about this. It used to be that you had to worry a lot more about calculating this on the AP exam. And you don't really need to worry about that so much. I'm going to step you through how to do it, okay, so that you understand it, but don't get super stressed about this. I'm going to walk you through it, okay? So here are the steps of how to calculate it. I don't even necessarily want you to copy these down right now. Don't even bother, okay? So we're going to practice using a really, really simple data set, okay? We've only got 5 different data points. Let's see, we're trying to figure out the spread on our carrots that we grew, okay? I'm going to calculate the standard deviation of this. So I'm going to put the steps back up. And what I want you to do is, using the steps, calculate the standard deviation of this data set. So here we go. Here's the data down here in the right-hand corner. Here are your steps. So take it step by step, walk through all the steps, pause the video, and then come back when you're done. All right, so hopefully you're done now. And did you get something close to like 4.5? I hope so, because that's what I got. I will show you the work just so you can see. Here's the mean. Here is all of our numbers minus the mean. And then we square them all. We add all of these up, and we get about 81.2. And then we do 5 minus 1, which is 4. 81.2 divided by 4 is 20.3. Square root of 20.3 is 4.51. So that's what I got, keeping this amount of decimals. Don't worry about like sig fig so much if you're like an AP Chem person, but if you got something close to 4.5, you're good. Okay. So hopefully now you see where it comes from. AP no longer requires you to do this calculation on the test, okay? They will give you the standard deviations already calculated, but you have to know like what to do with it and how to graph with it. So that's what the rest of this is going to focus on, kind of like what it means and how to graph with it. So this is like a look at a traditional bell curve. And here's our equation. You're like, what? It's okay. Just like take a moment. So what this means is we're looking for the average. So on this bell curve, your average here would be the 0. Okay, so this is like your average. That's where our peak is. And if you're plus or minus 1 standard deviation from your average, from your mean, that's going to include 68% of your data. So for our carrots, if our standard deviation was 4.5, if we take our mean plus or minus 4.5, that would get us from like 15.8 to 24.9. That would include 68% of our carrots. Okay. Now, if I do plus or minus 2 standard deviations for our mean, that would include 95% of our data. So we would take our SD, which is 4.5, times that by 2, which is 9. And so our range now is going to be our average minus 9 and an average plus 9. Okay, so this 2 here, that means standard deviation. So from here to here on our carrots, that would be like 11.3 to 29.4. This would include 95% of our data. And typically speaking, when we're talking about our data, we want to include 95%. Notice that the percent that we're not including would be kind of outliers. These are like the extreme low points and the extreme high points, but everything in the middle we want to cover. Okay, so almost always you're going to be taking your SD and timesing it by 2. Don't worry, you're going to get lots of practice with this. Just stick with me. Okay, so let's take a look. Just visually, which graph has data that's more spread out? Hopefully you're saying this dashed one, right? You can just see like the peak isn't as high, it goes wider. Yeah, and if we look up here, look at the standard deviation. For this dashed one, the standard deviation is 12. And for the solid one, it's 7. So you can see how a smaller standard deviation leads to like tighter data, and a bigger standard deviation leads to more spread out data, okay? So if we were to take this number and plus or minus 7 from it, go out 7 and out 7, that would give us 68%. If we were to take 52 plus or minus 14, that would give us 95% of the data, okay? So how this is going to work for us, though, is that when we're doing labs and stuff, oftentimes we're going to be graphing it, okay? So what you're going to do is you're going to make a graph of your data, and depending on your data, you're going to choose line or bar graph, okay? And we'll talk through how you can make that choice, but you're going to choose a line or bar graph. And then you draw in your standard deviations as these things called error bars. They're these little things right here, okay? So if my standard deviation was 1, okay, if I wanted to show 68% of my data, I would graph the average, and then I would draw a little bar up 1 and down 1, up 1 and down 1, up 1 and down 1, okay? Same thing for a line graph. But if I wanted to show 95% of my data and my standard deviation was 1, 1 times 2 is 2. I would then put my error bars up 2 and down 2 from my average. Okay? Does that make sense? I hope so. I hope so. Let's take a look at some real data here. Okay, so here we've got some fish and their length was measured, divided up by males and females. Okay, so let's take a look at this here. So what are some conclusions we could make by this? Well, let's take a look at which one has the more clustered data. Which one's standard deviation is smaller? Well, the error bars on the male is smaller than the error bars on the female, which means that the males are like more a similar length. There's more length variability in females. But notice how my error bars here and my error bars here don't overlap, right? So basically what this says is like the smallest female is somewhere around 17 millimeters of 95% females. But the biggest male is like somewhere close to like 11 millimeters, right? So if you have a 15 millimeter fish, it must be a female, right? There were no male fish that were 15 millimeters. So we don't have any overlap in our error bars, which means these two groups are statistically significantly different. So males and females, by the math, have different lengths, right? Does that make sense maybe? Okay. Let's look at this graph. Here it is with a line graph. We're looking at vitamin C with teeth growing in guinea pigs. I guess that's a thing. And we can give them OJ or ascorbic acid and see how much their teeth grow. Notice here if we have a dose of 0.5, OJ makes their teeth grow longer. Notice our error bars here are way above. So even the shortest tooth of these guys is longer than the longest tooth of these guys. So orange juice makes them grow longer at a dose of 0.5 milligrams. Orange juice still makes them grow longer at a dose of 1. But up here at a dose of 2, notice how our data is really close together and how our error bars overlap, which means once you get up to a dose of 2, these two things make teeth grow the same amount, and we would say that that's not statistically significantly different. Okay, there's no difference. Okay, so if you want to right now, a good idea would be to try to do a little practice. Okay, try going back to the carrots. Okay, and you use their average height which I just put down here in the corner. Okay, here's your average height. Calculate the mean. Create a graph. Think about if this would be a bar graph or what. My hint to you is going to be a bar graph with one bar. Okay. And then we already have our standard deviation, right? We know it's like 4.5. And then draw in your error bars to represent 95% of your data. Okay. And if you bring this to class, I'll show you what it's supposed to look like.